Okay, so we're doing iGCSE little intro topics. It's 3D part B, second part of, so it's sound waves. So we're already looking at light. So sound waves, you need to know about hearing ranges. So you need to know factually that for human hearing, it's 20 hertz to 20,000. You might not be able to hear that much, maybe as an adult, 14,000, but that's the typical quoted range. Above that is ultrasound. Other animals, it's different. So you've got ultrasound, you can see that's higher. The acoustic range is 20 to 20,000. Infrasound, we don't really talk about, but that's below. So between 1 and 20 hertz. So some very low frequency sounds are present on the planet as well, like earthquakes. Oscilloscope sound, we've got to understand how these screens work. So what do the squares up mean? So we're looking at amplitude and down amplitude as well from the middle. And we want to know how to work out what these little squares mean. So we're looking at divisions per second and volts, divisions for volts of the screen. So it's basically a way of seeing what's happening on the oscilloscope screen to show different sound waves. And so relating to that, we need to look at pitch and loudness. So pitch relates to the frequency of vibration of the source, lower pitch, higher pitch, so more sound waves in a given time. And the amplitude, we said, was the height. So it's either louder or quieter. You specifically need to know the concept of a longitudinal wave. So we talked before about longitudinal waves. It means that the particles move in a direction parallel to the progression of the wave. They carry energy from one place to another, and they have an amplitude and wavelength. And sound needs a medium to travel through and cannot travel through a vacuum. So we've got here a direction of particle motion, backwards and forwards. You've got the wavelength between compression and compression. And so you should be able to draw and label diagrams like that. We've also got experiments such as this. So there's two different experiments. You can hit a hammer on a bench and a microphone will pick up a start time, a trigger for a timer. And then the sound wave propagates through the solid and then it will trigger another stop idea, a little pulse on a microphone, and it will start and stop a timer. This one, 3.1 milliseconds. So I can actually work out the speed of sound with a hammer practical. We've also got another one, so I could have a signal generator and two microphones and a speaker. So I put the part and I pick up two waveforms. And what I do is I get it so that they all match up, and then I move the microphone a whole wavelength away, and the one wave at the bottom or the top, depending on how you've configured it, the wave will move across. You'll watch it move across. That distance then will effectively be the wavelength of the wave, and you can again work out the speed of sound. So you should be able to explain both practicals. There is another one where you could always make an echo on a wall, or you could clap two blocks together, let it go about 100 meters and then stop the timer. That's another way to work out the speed of sound, but you've got to be able to talk practically about different methods. There you go, that's sound waves in iGCSE physics.